So here's the way we solve the first practice problem. We're given a flux rate here of 2.5. So the precipitation rate here, P, is given as a rate of 2.5050 millimeters per day. And that's 3 significant figures. And so this is a flux. It has dimensions of length per time, and we are asked to calculate the volume that accumulates in a day, or a volumetric flow rate. This is a volumetric flow rate in dimensions of length cubed or volume per time. So the way we go between a flux and a volumetric flow rate is, the formula is that the volumetric flow rate is equal to the flux times the area over which that flux is falling. So with this flux of 2.50 millimeters per day, we're going to multiply that times the areas of these various vessels into which the water is going to fall. But the first thing we need to do is make sure that our units of length on both the flux and the area are the same. And right now the areas are all as square meters, but my flux is millimeters per day, so I'm going to have to convert my flux in millimeters per day to meters per day. And I can do that simply by dividing by 1,000, because there are 1,000 millimeters in a day. So the precipitation flux will equal 0.00250 meters per day. And then I simply take this value, the precipitation flux in meters per day, times these areas in meters squared. And when I multiply them together, I will get meters per day times meters squared per day equals meters cubed per day, which is what I want. That is the volumetric flow rate. So I'll start with this. Let's just do this swimming pool as an example, and then I'll just actually leave the rest for you to check. So this is equal to the volume of water that accumulated in the swimming pool will equal the flux, which was 0.00250 meters per day times the area of the swimming pool, which is 125 square meters, and that equals 0.313 cubic meters per day. Now I'm just going to write in the rest of these so you can check your answers, but the procedure is exactly the same for each of these other vessels. We multiply the flux in meters per day times the area in square meters to get the volumetric flow rate in cubic meters per day. And hopefully you can see that with the same flux, the areas of the vessels with the larger areas accumulate more volume of water, right? So the Pacific Ocean accumulates a vast quantity of water, a vast volume of water, compared to a coffee cup, which is just a tiny few, actually, cubic centimeters of water. That's just a tiny amount of water that will accumulate in the coffee cup from the same flux of 2.5 millimeters per day. Now, turning to the second problem, this is the same basic idea. Now, though, we are given a volumetric flow rate and we're asked to calculate the flux. So we're kind of going the other way now, but the idea is the same, right? So if what we wrote before, that the volumetric flow rate was equal to the flux times the area, then we can just rearrange this equation to show that the flux, which is now what we want, right, is equal to the volumetric flow rate divided by the area. So this is all we're going to do. We're going to calculate the flux by dividing the volumetric flow rate by the area. The problem here, as is unfortunately the case, is that in the US we have a whole lot of unit conversions to do, and that's what makes this such a pain. So the stream flow, the volumetric flow rate here, is in cubic feet per second, and the area is in miles squared. So the strategy is going to be to take the area and make that into feet squared, and then I will be able to calculate the flux, since now both the units of length here are feet cubed up in the volumetric flow rate and feet squared in the area, I can do that, right? So I'll now have a flux. All right, so let's go here. The flux will be calculated as the volumetric flux rate of cubic feet per second divided by an area of feet squared, and that will leave me with a unit of feet per second for the flux, and then I'm merely going to have to convert the units of feet per second to inches per year, which is what I ultimately want. So first, calculate the area of the watershed in miles squared to feet squared. Well, that's one of these things that's a pain in the ass. You can look it up. I'll just show you the answers here. If you have Excel, it's really easy. But otherwise, you'd have to look that up because you probably don't remember the conversion from miles squared to feet squared. So here are our areas converted into feet squared. And now I will show the calculation of the flux in feet per second, which I get by dividing the volumetric flow rate in cubic feet per second by the area in feet squared. And that is indeed the key calculation here. That's the crux of the matter. That is this calculation here. Flux is equal to the volumetric flow rate divided by the area, making sure that our units of length are using the same unit of length cubed and length squared, the same L here. In this case, it's feet cubed divided by feet squared. And then the last part of this problem is simply to convert these values in blue in feet per second into the different unit of inches per year. And that's actually just a matter of multiplying by the number of seconds in a year and then multiplying by the number of inches in a foot. And if I go do that, I end up with the final answers of 46 inches per year for the flux from stream 1, 68 inches per year for stream 2, and 24 inches per year for stream 3. And finally, we get to the last question, which is actually probably the easiest of the three. So here we are given again the volumetric flow rate, this time for evapotranspiration. So this here is a volumetric flow rate in terms of meters cubed per year. And we are also given the area in terms of meters squared. So we're using the same unit of length in both meters and meters squared and meters cubed, right? And we're asked to calculate the flux. Well, this again is just a simple transformation between volumetric flow rate and flux. So remember, the volumetric flow rate is equal to the flux times the area. So the flux will have to equal, just rearranging that equation, the volumetric flow rate divided by the area. And we are given both of those in the same unit of, using the same unit of length cubed and length squared in meters. So all we need to do is divide the volumetric flow rate in the second column by the area in the first column. And if I do that, I get the following. So I get so I just divide, I'll just write it out here. So I divide 3.45 times 10 to the 8th cubic meters per year divided by the area, which was 5.44 times 10 to the 8th meters squared. And when I do that, I get 0.634 meters. That was it. That's my flux, 0.634 meters per year. And if I do it for St. George, I get 0.957 meters per year. Again, I'm asked to actually do this in millimeters per year, and that's a conversion by now you should be able to do in your head. That's just 1,000 millimeters per meter. So we just moved the decimal point 3 places. So this is, I'll write it in blue, final answer here. This is 634 millimeters per year for Salt Lake City and 957 millimeters per year for St. George. And so we can see that St. George actually has more intense evapotranspiration. Even though the total amount of evapotranspiration, the volumetric flow rate, is so much smaller because St. George itself is so much smaller than Salt Lake City. But in terms of the intensity of the evapotranspiration, and that's really what the flux conveys, St. George has a higher intensity of evapotranspiration than Salt Lake City.